Forget basic induction. Today, we're dissecting the Autotransformer, a total topological marvel that redefines electromagnetic efficiency. Think about it. How do you exponentially amplify apparent power capacity while literally slashing copper mass in half? Standard transformers, they rely entirely on magnetic flux linkage across completely isolated primary and secondary windings. Kind of bulky. But autotransformers collapse this topology. They use a single, continuous winding, superimposing both circuits right at a tap. This shared node is genius. It allows simultaneous power transfer through both magnetic induction and direct electrical conduction. This elegant topological shift fundamentally alters the transformation ratio math, unlocking absolutely massive apparent power gains. Since direct conduction supplies part of the load current, your effective volt-ampere rating just skyrockets. It's beautiful. This gives us a remarkably compact footprint, handling drastically higher loads than any equivalent two-winding topology. Look at the copper volume equation here. Optimal weight depends entirely on our voltage transformation ratio, A. Here's the golden rule. The closer your primary and secondary voltages are, the greater the material optimization. If you have a high transformation ratio, say 10, your copper mass savings are a negligible 10%. But as that ratio approaches unity, like 1.1, boom, you unlock a staggering 90% reduction in copper. So, the trade-off? You gain immense efficiency and low leakage reactance, but you completely sacrifice galvanic isolation. Tracing the internal nodal currents reveals an inherent vulnerability. It all comes down to this shared grounding. If that common winding fault's open during step-down, your load gets hit with catastrophic full-source overvoltage. Despite that risk, their ruggedness handles extreme transient spikes, driving arc furnaces demanding over 100,000 amps. They perfectly tie massive synchronous power grids together, right where those differential voltage ratios are incredibly tight. Physically, this specific hardware dominates industrial control equipment and localized voltage boosting systems across the board. They also act as dynamic boosters, providing essential impedance compensation in heavy electrical traction and railway networks. Plus, they execute reduced voltage starting from massive induction motors, safely mitigating those destructive in-rush current transients. To summarize, autotransformers completely bypass traditional limits through conductive superposition and shared magnetic flux pathways. This delivers theoretical maximums in material optimization, provided your system voltage ratios remain tightly bounded. The ultimate paradox. When does an exponential leap in efficiency justify the catastrophic risk of zero isolation?
Welcome to CAT 017 Learn. If you find this content helpful, please make sure to hit the like, share, and subscribe buttons below.